This problem provides us an opportunity to both work on some gas law scenarios and do some review of other material from first year chemistry. Octane, C8H18, is a hydrocarbon. All hydrocarbons, when combusted, which means they react with oxygen to burn, will produce carbon dioxide and water as the products. So this would be an example of a combustion reaction of a hydrocarbon. Next, we have to balance the equation to make sure we have the same number of all of our atoms on the reactant side as we have on the product side, which follows the law of conservation of mass. To start, we have 8 carbons to match with our 8 carbons we have in the octane. By putting a 9 by the water, that gives us 18 hydrogens to match up with the 18 hydrogen in octane. Right now our carbon and our hydrogen atoms are both balanced. Now 8 times 2 in our CO2 gives us 16 oxygens, and our 9 times 1 in the water is another 9, so we have 25 oxygen atoms to account for. O2 is an even number, and here we have 25, so what we can do is start out and put a fraction and balance the oxygen with 12.5. That gives us 12.5 times 2, which gives us 25 oxygen atoms, and we're now balanced. We'll adjust the equation now so we get all whole numbers for our balanced equation by taking the entire equation and multiplying by 2. This now gives us our balanced equation for the combustion of octane. Let's a reminder what the balanced equation will tell us now. It gives us the ratio in which the reactants must react and the products are formed. If we have 2 molecules of octane reacting with 25 molecules of O2, we're going to produce 16 molecules of CO2 and 9 molecules of H2O. For chemists, it's difficult working with molecules individually, so the quantities that we'll use is the relationship of moles. Same thing as 2 moles react with 25 moles to produce 16 moles and 9 moles of our water. However, we're given octane in mass of 2 grams. So our first order of business is we have to switch the mass of octane to moles of octane so we can then use our ratio from the balanced equation to determine how much oxygen we'll need to react with all of our octane sample. From the periodic table, we can find that the mass of carbon is 12 grams per mole. We have 8 carbons in our octane sample, so 8 times 12 would indicate that a mole of octane will contain 96 grams of carbon. Repeating the process for hydrogen, where the mass of hydrogen is 1 gram per mole, we have 18 hydrogens in our sample, gives us 18 grams of hydrogen in 1 mole of octane. Adding the 96 and 18 gives us a mass of 1 mole of octane of 114 grams. We can now use the mass of 1 mole of octane to set up a proportion, and that we know 1 mole of octane has a mass of 114 grams. And if we know that we have 1 mole of octane per 114 grams, we can solve for X moles of octane present in our 2 gram sample of octane. Solving for X, we find that our 2 gram sample of octane represents 0.0175 moles of octane. Now we can again use a proportion to solve for how many moles of oxygen are needed to react with our octane sample. From our balanced equation, we can see that 25 moles of oxygen react with 2 moles of octane. We can use this to set up a proportion, saying that we have 25 moles of O2 per every 2 moles of octane. We now know then we can set this up so we have X moles of oxygen per 0.0175 moles of octane. This will give us how many moles of oxygen are required to react with our octane sample. Solving for X, we find the number of moles of oxygen required to react with our octane sample is 0.219 moles of oxygen. Now that we know our moles of oxygen, we have a temperature for the oxygen, we have a pressure for the oxygen, and in the ideal gas law will be a number of moles. We can solve for the volume of oxygen that would be required to react with our octane sample using the ideal gas law. Rearranging to solve for volume, we have V equals nRT over P. We have to remember to convert our temperature to Kelvin. To do so, we add 273 to our 50 degrees Celsius, giving us a temperature of 323 Kelvin. Setting up our ideal gas law, our number of moles of oxygen is 0.219, our gas constant is 0.0821 liter atmospheres per Kelvin mole. We have 323 Kelvin for our temperature and 1 atmosphere for our pressure. We can now solve for our volume of oxygen required to react with our octane sample. Solving for V gives us a 5.81 liter sample of oxygen, and that's what would be required to react with our 2 gram sample of octane.